All right, so sad day. We got the last day of the two-dimensional motion unit before the test coming up here. So let's go over the last couple challenging pages here. The rest of the packet after this are all ACT, SAT kind of style passages, which you can kind of read through. These will be the last ones that we actually explain. All right, so number 26 here. Ball's thrown from a roof, lands 50 meters away, 0.79 seconds later. What's the horizontal velocity right before hitting the ground? In most problems we started with the dy, but in this case we know that it lands 50 meters away, so we're dealing with something in the x direction, a component in the x direction. We know that our time doesn't matter if it's in the vertical, so to speak, or horizontal times time. It's a different dimension from space altogether. That's a whole other topic for another day. That'll blow your mind. But we have our distance in the x, we have our time, so we can use this formula, distance in the x, and time, to figure out what our velocity is. Now, right before hitting the ground, that's actually everywhere. So not only is it 63.29 meters per second right there, but it's also 63.29 meters per second there, and really all the way up to the beginning. Because again, we're talking in the horizontal direction. The only thing acting on our projectile is gravity. Gravity doesn't act in the horizontal direction, therefore our projectile is not going to slow down, it's not going to speed up. Alright, so let's go ahead and take a look at the next one here. What's the vertical velocity right before hitting the ground? This one, it is a different story. Our vertical velocity is going to be constantly changing, right? At the very beginning, it's not going to be traveling down quite yet, so it'll have a initial velocity of 0, which is why we can get away with a 0 over here. But then as it makes its trip, it's going to go faster, 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 even faster, as we go further and further and further, as we get further and further and further towards the end of our flight. Okay, so our initial velocity then, again, that's 0. It hasn't started falling at its initial point where it's just sitting there. Our v final we're not sure of, but we do know that our time, it took 0.79 seconds to hit the ground in the vertical direction, so it also took 0.79 seconds to hit the ground in the horizontal direction as well. So we know accelerations from gravity, we know our time, multiply those guys out, and we come out with negative 7.74 meters per second. And the negative should make sense because we are going down at that point. Right before hitting the ground, we are in the downwards direction, so negative's good. All right, how high up is the roof in this case? So again, we kind of have our little building over here. We want to know, well, how high up is this thing that we've thrown a projectile off of? Okay. Well, in order to do that, we know that if I have my time, I can figure out what my height is, right? Because time will work with any one of our formulas, but if we're looking for how high up, we're looking for dy. Again, this would be dy right here if I'm looking for how high up that projectile was. So I'm going with my formula that has dy in it. From there, go ahead, plug in all your variables. To begin with, careful, because we did solve for a velocity over here. This velocity is in the x direction, so we do have an initial velocity of 63, and some students are going to put 63 here, but we also have an initial velocity of 0 in the y direction. We want the velocity from the y direction, so that's the one that's 0. The 0.79 is not really going to matter here for our time because it's going to be 0 times 0.79 anyway, so we could even get rid of that, or leave it in if it freaks you out to get rid of it. The back half is from the formula. 1/2, negative 9.8 is from gravity, and then the 0.79 squared is from t squared. So I would recommend doing this first, t squared, then multiplying by this, which is negative 4.9, and you'll come out with 3.06 meters. So it's 3.06 meters tall. The only reason that it's kind of a challenge problem is because we haven't seen one like that before, at least not very often as compared to some of the others. 27 for projectile launch horizontally. What can we say about the horizontal velocity? We already talked about that. It's always going to be constant. Whatever final horizontal velocity is, it's also going to equal whatever our initial horizontal velocity was, and everywhere else along the path of a horizontally launched projectile. Let's take a look at some of these conceptual problems. 28, 29, 30. So 28, if the projectile were launched at an angle up, how would it affect the total time? Now, if we didn't launch at an angle up, just threw it straight out, or just dropped it straight down, these two, whether or not I threw it horizontally or dropped it straight down, these two types of projectiles would take the same amount of time to hit the ground because both have the same y distance. In this case, if I were to launch it up at an angle, I would take a longer time because I still have to fall the same distance here, but I also have this initial there's this initial little arc that I've got going on here. So it's almost like an arc problem and a cliff problem together. It takes time to get up here, takes time to get down here, plus all this time that it normally would have taken. So I've got to add all that up. For project 29, if a projectile were launched on an angle down, how would that affect the total time in y? Well, again, if I were just launching it straight out or dropping it straight down, either way, those are both going to take the same amount of time. But then if I actually throw it straight down, either throw it straight down or throw it at an angle down, I'm going to have a shorter time because I'm essentially it's almost like I'm helping gravity out. I'm giving it an initial velocity in the downwards direction, plus gravity is also going to be pulling it down, so it's going to have a fairly short time in comparison to had I just dropped it down or had I thrown it horizontally and it also come down. Number 30 is a swimmer dives off of a cliff that's 78.4 meters above the Pacific Ocean. So that's what I got going on here, 78.4 meters above the Pacific Ocean. There would be my cliff. I got my little swimmer here. By the way, this is a really bad idea. You don't want to dive that high up. Not that you really have the opportunity to around here anyway, but you know. All right, his horizontal velocity is 4 meters per second. So going this direction, it's 4 meters per second. We know it's 4 meters per second everywhere along this guy's path, this swimmer's path here. All right, and again, the vertical velocity will change, but the horizontal velocity will stay the same. Okay, so how long did it take him to hit the water? Well, think about this logically. You know, if the cliff's taller, it's going to take him longer. If the cliff's shorter, it's going to take him less time. So we know that distance in the y direction is the thing that time depends on. So distance in the y direction, I have that, and I can figure out my time based on that. Nice thing is, the first part of this formula we don't need because velocity initial is going to be 0. Again, don't go with 4 meters per second as my velocity initial. This is my velocity x initial. I want my velocity y initial because I'm dealing with a y component. So I've got to keep all my components together. Y's with y's, x's with x's. Even for the males. Get it? Chromosome joke? No? Alright, so anyway, we've got 78.4 meters high for our distance in the y direction. The 1/2 and the t squared are part of the formula. Negative 9.8 is coming from gravity, so from there, go ahead and solve. All right, so 78.4 equals negative 4.9 for this part of my math. And then from there, I would divide 78.4 divided by negative 4.9 to get t squared by itself, which would be 16. Take the square root of both t squared and 16 because I don't care about t squared, I care about t, so get rid of the squared by square rooting. That's even a word, and then I come out with square root of 16 is 4. This one we should hopefully be able to do in your head. Alright, so how far out does his dive take him? Well, now we're dealing with things in the x component, so all of our numbers have to be in the x component, whether or not it's distance or velocity. Well, our distance, we don't know, that's what we're trying to figure out, but our initial velocity and our constant velocity is 4 meters per second in the x direction, so that's what I got going on here. And then it just so happens that these numbers are the same. It's not always going to be like that. But my time was also 4 seconds, and again, time doesn't matter because it's outside of space, so it's not part of one of the dimensions, either x or y. It's outside of it entirely. Links them together. 4 times 4 is 16 meters. And again, slow these videos down if you need to, rewind them, do whatever you need to feel comfortable. 31. So we've got this man that's driving his car along a rural road. He becomes distracted, doesn't see a road closed sign, realizes that there's a 10-meter ditch that he's approaching. So that's what I got going on here. We got from here to here is that 10-meter ditch that I'm dealing with. Instead of braking, he accidentally raises his speed to 30 meters per second. Bad move. Don't know how that happens, but that's what I got going on here. This is from raising his speed to 30 meters per second. So that means the moment he leaves this cliff or bridge or whatever the heck it was, this road, he is going at 30 meters per second. He can't slow down. He can't speed up once he's already in the air. So that's his initial x velocity, right? We may even want to say v initial x or VO, right? V naught x equals this 30 meters per second. Vy going down, his initial Vy is 0 meters per second because he's not going down at first. It's not until he's off the cliff that he is. All right, so he raises up to that 30 meters per second. If he continues at the same rate, which of course he would, will his car make it over the ditch to the other side where it's 10 meters lower? There's a couple ways to do this problem. The first way would be to, no matter what, we've got to figure out the time. So we're going to have to deal with the y direction. Well, I know the distance in the y direction, he's going to be falling for 10 meters. Either way, he's not going to make it, but let's just see if he goes across the ditch at least. So I know that I'm going to be dealing with this distance in the y direction because he's falling a y distance. And again, the thing that time depends on, the component that time depends on, is the vertical direction, because gravity is the thing that's actually pulling me down and eventually going to stop me when I hit this ledge, or hopefully hit this ledge, right? So initial velocity down, 0 times time. I don't know it, but again, 0 times time's going to be 0. 0 times anything, including a variable, 0. And then 1/2 and t squared are part of the formula. At this point, I do know gravity, right? Even though it doesn't tell me, I'm assuming this is on Earth. 1/2 times negative 9.8 is negative 4.9. Go ahead and do our math. 10 divided by negative 4.9 to get t squared by itself. Leaves us with t squared equals 2.04. We don't want t squared, we want t, so we square root it to get rid of the squared, and I come out with a time of 1.43 seconds. So that means that it's going to take him 1.43 seconds to travel both the horizontal way and the vertical way. So 1.43 seconds in his total time to travel. Okay, so now there's a couple ways we can do this. We can say, well, let's go with his let's go with this 10 meters. We can think of it as, does he clear it? So let's not worry about the fact that this is 10 meters quite yet. Let's just solve for a horizontal distance and then compare. So if my initial horizontal velocity is 30 meters per second and my time is 1.43 seconds that it takes him to fall, multiply those two using dx, because again, I'm dealing with the x component, so I've got to deal with an x equation. This is the only x equation that I have. So 30 times 1.43 gives me 42.9 meters. So does he make it past this 10 meters? Oh, definitely, right? He makes it with 32.9 meters to spare because it's 42.9 meters total. So yes, he definitely makes it over. The other way we could think about it is, well, let's compare it to our time. Let's say, all right, well, I know I want to make it at least 10 meters. Well, let's use 10 meters for my distance. So 10 meters for my distance. I know my velocity is 30. So knowing that my distance has to be at least 10 and that my velocity is 30 in the x direction to begin with, how long would it take him to get over a 10 meter gap? Oh, well, it would take him 0.33 seconds. Well, he was in the air for 1.43 seconds, though, which is definitely greater than 0.33. So he makes it. Either way, you don't have to know both of these ways. Use either this way or this way. It just depends on what makes more sense to you. But either way, we see that it does in fact get us over the cliff. Now, 10 meters is about a little more than 30 feet, 35 feet or so. So either way, he's probably not going to be doing so hot despite clearing the gap. Sorry, kids. That's a downer. All right, 32. Mr. Fred's parachuting out of a plane, going 400 meters per second, so he's going in this direction. He sees the target area approaching, knows his altitude's 5,000 meters, so that's what I got going on here. This altitude of 5,000 meters, we're considering that our dy direction, right? This is considered our Vx, velocity in the x direction. We want to know how far away from the target must he jump to land on top of it. So this is almost identical to your Marble Lab, where we were trying to figure out how do we hit the target with our launcher. All right, so I don't know the distance in the x direction. That's what I'm trying to solve. Well, remember what's time dependent on. We're always going to need to know time, no matter what. What's time dependent on? It's dependent on nothing to do with the horizontal direction, everything to do with my vertical direction, because gravity acts in the vertical direction, and gravity is the thing that's going to pull it down and make it hit the ground. So I know that he's falling for 5,000 meters. So that's what I'm going to use to figure out my time. Well, what's the only one of two formulas that I have for the y direction is either the dy formula or the v minus v naught formula. Well, v minus v naught doesn't have distance in it, so that leaves me with this formula that I have to go with. So I know my distance in the y direction. That's right over there. My initial velocity, careful, is not 400. It is 400 in the x direction, but not in the y direction. Remember, we got to break everything down into components. So my y direction initial velocity is 0, because I'm not quite falling yet. If the man's standing in the plane, he is going 400 meters per second along with the plane. But if the plane's not going down, then he's not going down, so 0 meters per second down. So I can get rid of this first part of the formula. Notice that can happen quite a bit. If in doubt, you're probably okay to get rid of the first part of the formula. Not every single time, but if you're in a pinch and you're like, what do I do? Most likely you can probably get rid of that first part. So the 1/2 the t squared, that's part of the formula. Gravity there. So 5,000 divided by negative 4.9. The negative 4.9 comes from here, 1/2 of negative 9.8. 5,000 divided by negative 4.9 gives me 1,020. Well, that's t squared. I want t, so let's get rid of the squared by square rooting, both sides. And that means I'm going to fall for 31.94 seconds. Well, if I know that I'm falling for 31.94 seconds this way, I also know that I'm going for 31.94 seconds this way as well. Because again, time is the thing that relates all of my formulas together, because time's outside of the other dimensions. All right, well, if I want to know how far he's actually going to go in that 31.94 seconds, I'm dealing with, for how far, an x component. So dx equals v times t. I've got my velocity, I've got my time. So then from there, multiply them out. And if you use the that second comma, which is second negative, which is the answer key in the calculator, rather than actually typing it as 31.94. When you multiply these two numbers, because this is actually a really long decimal, you come out with this exactly. If you type it out as is, how you see it in my answer key, you come out with 12,776. And that's fine too. It just, like it says, depends on your rounding. Hey, hopefully you felt okay with this one, because again, it is very similar to the lab. All right. Last one's a real weird one, but we'll go over it. So 33, circus clown's fired out of a cannon. Its velocity is 500 meters per second. So it's velocity in the x direction. Right? Initial velocity in the x direction. Initial velocity down before he's fired out, or right as he's being fired out, is 0 meters per second for the initial y. He's coming off this 100 meter tall platform, so that's where I'm getting this 100 from, up there. It lands in a net 4 seconds after takeoff. How far from the ground is the net? So this one's a hard one. It is an arc problem, right? Basically, we've got an arc happening here. Although we're not dealing with the entire arc, we're only dealing with a portion of that arc. So that's kind of that's a challenge. That'll be a bonus question on the test like this. Not a ton of them, so don't feel like if you don't understand this that all is lost. But do realize this: we know that the platform's 100 meters up, but it doesn't say that it took him 4 seconds to hit the ground. It says it took him 4 seconds to hit the net. Well, the net's not on the ground, so it's not going to be 100 meters. So what I'm going to do is, knowing that I have 4 seconds to fall, I'm going to figure out the distance that he fell in that 4 seconds. Well, initially, he's at 0 meters per second in the y direction, falls for 4 seconds, so this part's not going to matter anyway. 1/2 the t squared is part of the formula, so 4 squared. So 1/2 times negative 9.8 from gravity times 4 squared for our time, that gives us 78.4. Like I say here, this represents how far he fell. So what this number represents, maybe I'll switch over to a highlighter here. What that number represents is how much he fell here. Okay, so again, not all the way to the ground, but from where I highlighted there, from here to here. Well, we still got this distance that we need to figure out how high up the net is. Well, if he fell for 78.4 meters and the platform's 100 meters off the ground, that means that we've got 21.6 meters left over from wherever he fell to the ground. So that means that the net must be 21.6 meters up there. Take a couple looks at this problem. It's not going to make a ton of sense the first time around unless you're really gifted, which is awesome with math, at least. If not, though, take a few looks at this. There's no shame in doing that by any means whatsoever. All right, so last one, weird one. America's been taken over by giant frogs. This is definitely a Miss Mardoian problem. Each frog has a horizontal component of 400 meters per second and a vertical component of 98 meters per second when they jump. How far does it go in 3 jumps? Well, there's like 10 different ways of doing this problem. Probably the easiest, though, is just to figure out how long does one jump take them and then go from there. So really what I've got going on is I've got this giant frog that's jumping up, has an initial vertical component of velocity, at least, of 98 meters a second. Wow. Has a horizontal component, which would be the same throughout, of 400 meters per second. Even more impressive. So these guys are cooking. It takes them a certain amount of time to get up there, a certain amount of time to get down. Now, if I don't know my distance, I could solve for it, but I don't need to. I know my initial velocity in the y direction, and the reason I'm using y direction here and not the x direction is because, again, the thing that's going to depend on how long they're in the air for is how high up they get, right? Higher up they get, the longer they're in the air for. The lower down they get, the less time that they're in the air for. So v minus v naught is the go-to equation for this one, because again, the other equation that I could use is the dy equation. I do know my initial velocity in the y direction. I don't know my time. It's 1/2 a t squared, but I could figure out my time with something else and then go to my distance from there. But again, it doesn't ask me for it, so let's not worry about it. So v minus v naught it is. That's the only other option I have for my y direction. Well, I know my initial velocity up. I also know my final velocity. Right, my final velocity is going to be the opposite of my initial velocity. It's going to be just coming down, so negative 98 meters per second for v final in the y direction. That is a backwards y, but it is also 12:30 at night. So we've got a total of 20 seconds here that it's going to be in the air for, which makes sense. That means that it'd be 10 seconds up. Well, notice this is 98 meters per second. You'd be losing 9.8 meters per second of speed every second that you're in the air for. So it makes sense that it would take them 10 seconds to go up, If it takes them 10 seconds up, it's also going to take them 10 seconds down. Or forget all that and just go with your math and realize, oh, well, negative 196 divided by 9.8 gives you a time of 20 seconds. That's for one jump. It says that they do 3 jumps. So that would mean that they're in the air for a total of 60 seconds. So if we wanted to figure out our total horizontal distance after 3 jumps, we just use 60 seconds. Our v initial in the x direction is actually going to be our v everywhere for the x direction. So 60 seconds times 400 will give you that 24,000. Or do it the other way that I have it here in the answer key. Realize that now we're dealing with the x direction because we want to know how far they got. Our velocity is 400 meters per second. Time would be 20 seconds for one jump, so that's 8,000 meters for one jump, and then multiply it by 3 and you get 24,000 meters either way. So either way you take a crack at it, you get to the same answer there. All right, hope that helps.